This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right. Good morning, everyone. A few announcements before we start. Next week is teaching break. That means there will be no teaching, no workshops, and no consultation hour. Then mid-semester test solutions I have already posted. They are in the feedback and assessment. You can have a look. We are almost done with the marking, so we will post the results soon, maybe during the break, if all goes well. That's the second thing. The third thing is the workshop, machine learning workshop. It's a long one, so I decided to also, we are falling way behind in terms of the material, so there's a slight misalignment. So we address that by giving you one more week after the teaching break, and then the report will be due the end of the week after the teaching break. So that gives you 2 more weeks to work on the workshop. Things don't have to be perfectly aligned, you know. It can be, one of them can be ahead of the other. That's fine. You can catch up with the theory afterwards. So, and therefore, I was going to have no workshops last week of the semester, so in this case we will have workshops last week of the semester. But I'm making sure that the last 2 workshops are shorter. So there will be shorter workshops, couple of questions only. Maybe the last one will be more design-based. So, but a short one, not a long one, so you will be able to finish them in a couple of weeks. So I'm kind of, now that I planned the subject, you know, before encountering the student, and no plan survives the, you know, the reality. Once, so now I know better what capabilities of the students are. So next year it will be much more well aligned. So this is the teething problems, so to say, of the first edition. So, but I think we are in good shape. And any questions or anything I missed? Any comments? All right, so that's the situation. And then we continue with the material. Some of the basics of machine learning we finished today, and do the unsupervised learning, and start this week, tomorrow or next week, and cover the supervised learning. And then we will go to neural networks of different kinds, and then we will do a little bit of reinforcement learning, and then finish the subject. There will be a guest lecture, and that covers it. All right, so a lot of probability today. So as you might have guessed, we were been talking about, and these are the fundamentals: maximum likelihood and maximum a posteriori probability. These are embedded also to deep learning. Like, this is classical inference, of course, plays a huge role in machine learning, and then also in deep learning. So let's start. Okay, the idea here the idea is very simple. A common assumption in estimation theory. So we will make this assumption out of necessity, mathematical necessity. It's a modeling assumption. In reality, data is not IID. And IID means independent and identically distributed, right? So this assumption is constantly made in signal processing and estimation theory, that the data points are generated by a distribution, underlying distribution, and each data point is independent and identically distributed. So identically distributed means each data point is generated by the common distribution, and then they are independent of each other. They are just generated one by one, or in a batch, but in an independent way. That simplifies things in this way. So mathematically, it boils down to, so you have these n data points, right, conditioned on some parameters. So, this is the parameters of the underlying probability distribution, for example. So maybe it's Gaussian, then it's the mean and variance. The theta is mean and variance as two-dimensional vector. And then you have endpoints generated. What's the probability of encountering these n specific points given the underlying generating distribution, right? If the data points are not independent, this is all you can say about it. There is a joint probability distribution like this, right? But if they are independent and identically distributed, then things are much nicer, because then you can write this joint probability distribution as the product of individual distribution, probability distributions, and because they are identically distributed, the product becomes really simple like this, and that creates helps us a lot in the analysis, as you will see. Right? So you must have done this before, right, in probability. Now it's a good refreshment. So all right, but we do it now for a purpose, right? We are not learning probability for probability's sake. We are doing something for the purpose of learning things. So for data x, like x1 to xn, the parameters theta, right? We don't know them, and there's a model m. So that's also important. Sometimes it's implicit. Some of the books or material may not mention it, but there's always a model. There's either a probabilistic model or some other type of model that we are always saying. So that model is also underlying, is an assumption we make. We choose the model first, and then the model has the parameters, and then there's the data, and from the data we try to find the parameters of the model. If you choose a different model, the parameters will look different. So the Bayes rule, if we ignore the model, it's just this. So the posterior, theta given x, what's the probability of theta given x? I look at x, what's the probability of the theta parameters? I can write it using the Bayes rule as px given theta, what's the probability of x given theta, times p theta, that's the prior, what's the probability of theta being something, divided by the probability of the data itself. Right? But if the data is given, then this px is already known, observed, and the prior, you may or may not have a prior on the parameters themselves. If you don't know anything, then they are equally probable, uniform distribution, right? So then you see the posterior and likelihood, they are almost the same if the prior is uniform, and that's the main one of the main things. You can also write the same thing in terms of also adding the model into the picture. So then everything is conditioned on the model. But that's already, as I say, an implicit assumption we make. The moment you choose a model of any kind, you are conditioning everything on the model. So most of the books skip this part and just write it cleanly like this, but it's also okay to write it this way and keep that in mind, that we always pre-select a model M. Then given the model M, the problem is to find the parameters theta. Yep. And that's the whole thing, learning thing, learning a distribution. Probabilistic, from the probabilistic view. So maximum likelihood or maximum NMAP, maximum a posteriori probability estimation, a posteriori probability distribution, that's Latin, after the fact. The probability estimation is simply I maximize with respect to theta the probability of theta given the data set and the model. Given that I choose a model and I have the data set, what's the probability that theta is this and what's the probability theta is that? That probability, I want to find the maximum of it, because then that's the most probable, parameters. And then most probable parameters are kind of my best estimate, right? By definition. If I maximize that probability, that gives me my best estimate. Again, if I write it this way, with M also taken into account, you see here this denominator actually doesn't play a role. Then if I have a prior, if I suspect that certain parameters values are more probable, then actually I can take it into account here. You see? Because I multiply x given theta with this. So this is also taken into account. But if it's constant, probability of theta given m, all of the parameter values are equally probable and uniform distribution, that means I don't know anything about the parameters, I have no prior knowledge, I have no beforehand knowledge, then this is constant, the denominator was constant as well, so the this is then, we call it maximum likelihood estimation. And then only thing left is then theta maximum likelihoods are maximize the theta and the theta that you find by maximizing the probability that x given theta and m. And that's the right-hand side, right, from the Bayes rule. And that's it. So both are equivalent if the prior is uniform. If the prior is not uniform and you have beforehand knowledge, prior knowledge that some parameter values are more probable, maybe domain knowledge or some experience before you solve the data set, then you do this map. Otherwise, if it's uniform, then it's the same map is same as maximum likelihood, and maximum likelihood is simply this probability. What the maximum likelihood is probability that what is given the theta, I'm maximizing the probability of seeing this data set. Right? It's just the twist, the upside down. Right? Again, the denominator doesn't play a role, because if I'm given a data set, then that probability of that data set is already determined. I can estimate it at least. So and it doesn't have a theta in it, so there's nothing to optimize. It's a constant, goes out of the optimization problem. These optimization problems are also unconstrained. So, there is no constraint on theta unless something is imposed. So you have good old unconstrained optimization that we very well know. And then we find the theta star, and that's my likelihood parameters. Then I have learned the distribution, because then I know the parameters of the distribution. All right? Any questions? No? Let's do an example. This is a good example. It's a bit long one, so I will start and show the fundamentals first, and then the details. We have the solutions anyway. Let me go to the basics. And here, maybe zoom in a bit. Yeah. So I created my cheat sheet here myself. Map is here, the definition, and I have written my Bayes rule. So we have a random variable, x, that is normally distributed, right? And with mu being the unknown parameter, so the mu of the mean of the normal distribution, though, is defined by the Rayleigh PDF, Rayleigh distribution. That's also given. If you ask what is Rayleigh distribution, that's Rayleigh distribution. So that's that. What it asks is show that the maximum a posteriori probability map estimate of mu is given by this, and z is a long expression, and r is a long expression. But then nothing other than simple algebra is used to get these results. So first, we need to write it. We assume that the data is IID, so we kind of make this assumption. Let's solve it together. Assume data is IID, right? Independent, identically distributed. That makes our life easier. And then we have n delta data points. So we need to write this down as the probability, right? So how do we write it down? This will be then, let's write it down, mu map, right? I'm going to, because theta is mu now. Theta, the specific parameter is mu. Mu map will be what? Then that will be the argument of the maximize with respect to mu. And then I'm just looking at it, right? So that will be then probability of x given theta. And I can skip the m. M is, the models are given. We are looking at the normal distribution, and then the unknown parameter has a Rayleigh distribution. So the px given theta is normal, right? So this is important to note. Note that px given theta is normal, right? As given, right? And then p theta is Rayleigh. So maybe I write it like verbally. So So this is normal and Rayleigh. And both are given, right? Both were, I have given both of them. The distribution. They are given in the question, so they are here. So this is this, and the other one is this. So these are. Then I just write it down. So all I need to do is p x given mu times p mu. I'm ignoring the m because model is already chosen. I'm simplifying, and the px, right? But px is also because x is given, px is automatically given, and px doesn't have mu in it anyway, so this is a constant. Notice that this is constant, right? Doesn't play a role in this optimization problem. Only the terms x given mu and p mu play a role in the optimization problem. And if I write them down, so that will be then argmax. Then let me write it this part. Then this is equal. Argmax. What do I have? Pxu. So I do the IID assumption. So I can write this as a I equals 1 to n observations, and then it would be then pxi given mu and sigma square. Sigma square is known. That's not something we are looking for, so that can be even ignored. Maybe keep it simple. Let me write it as this way, and then p mu, right? But that's also given. And then I can write them. Then next step is I need to write them down. We can also write this as the likelihood function. The likelihood function is this. So this is the L. And we can also write, we can find log likelihood, which is, let's call it L equals ln or log L. Log L. Right? The log of, because if we maximize the log function, they are the same. Log is a monotonic transformation, the maximum will be the same. The value that reaches the maximum will be the same. Of course, the maximum values will be the log of it, the value itself. So then I can write this as the L equals, log L, which is defined as this. That will give me then this, the good thing about it is it will make the product sum, right? So then the first one, this becomes then the log p u, right? Plus the sum becomes, let me make it crystal clear, right? So this goes here and this goes here, right? After we do the log. So we got the sum. Now I equals 1 to n, and then we got the log p xi given mu. I know already the sigma square, so I'm kind of skipping it. All right. So then I can write this as, now we put the write the actual equations, the distributions. Right, so, and then once you write the distributions, p mu is given here, so you take the log expectation, so we get the, I'll just write this way, ln mu minus mu square over 2 sigma square mu from the Rayleigh distribution minus ln sigma square mu, because it's in the denominator, right? This comes directly from here, right? Okay, and then the other part is plus this is because this is normal also. Remember, this is normal with respect to mu sigma square, right? We know that, therefore we can write it that way, and then that would be the sum, and I equals 1 to n. ln 1 over square root of 2 pi sigma, and then minus log removes it. I wrote it as ln, sorry about that. So log ln, the same thing here, xy minus mu square over 2 sigma square. All right? Yeah, I should actually make these things consistent. Otherwise it looks very confusing. This is log, this is log. I used the log here. The other solution uses ln. That's fine. Okay, now note that what do we have here? These are, we maximize with respect to mu. So if you look at the terms, when you take the second derivative, this is quadratic in mu. Log mu, derivative is 1 over mu, second derivative will be minus 1 over mu square. And then here we also quadratic in mu, right? So we get we just go over the optimization, and then in the interest of time, I'm not going to spend too much time. So, but like we have essentially a straightforward convex optimization problem. And I refer to see the typed solutions, which I'm going to switch now, right? So we have this simple L of mu that we are trying to minimize with respect to mu, and it is simple in mu squared. Other terms are just constant. They don't play a big role. A lot of them are constant, so they will zero out when you take the derivative with respect to mu, partial derivative with respect to mu. So the solution actually is quite straightforward. As I said, in the interest of time, let me get the solution out. That would be this one. Yep, question 4. So if you go this way, let me see. So this is the derivation that I did, right? And then I stopped here. The next step is I take the derivative with respect to mu. It turns out second derivative is positive, so you have as I said, convex optimization problem. So the first order condition is not only necessary but also sufficient. And when you take the first order derivative, you have a 1 over mu here. That will create some quadratic term in mu, right? And then the log goes to 1 over mu, so it disappears. So it's actually the first order necessary and sufficient condition creates a second order equation in mu with mu square. Therefore, you use the basic algebra. Mu is a scalar. Basic algebra to use the formula to solve it, and that will give you the plus minus with this. And mu is because it's the mean, it cannot be negative. We have this mu greater than 0 condition because the Rayleigh distribution is positive. So therefore, we got this result that's just after a few simple steps of regular algebra. It's just the ax squared plus bx plus c, right? And then you find the x. In this case, it would be mu. That's high school algebra, right? So that's the rest of the question, and I'm going to post this. So there's no need to lose time with that. But what we have done is important. What we have done is, when we go back to the original question, so we have taken and we have done the maximum a posteriori estimate. The interesting part here is, for some reason in this question, right? So we know that the mean has a Rayleigh distribution. The mean mu of the normal distribution has a Rayleigh distribution. Therefore, I not only take into account this, but also multiply it with that p mu, and that is the whole formula of the map, right? So I have this, but I also have this, which is different from uniform. Therefore, I have taken both of them into account, and because this is constant, it didn't play a role in the optimization problem. Okay, good. So that's the story with that. And then but usually you don't have this information, right? You don't know whether theta will be more likely to have this value or that value. So in the most of the cases, theta can be anything, and theta can be anything means uniform distribution. That's another way of saying I don't know, right? So it can be anything within the bounds that I'm giving. So it's uniformly distributed. If it's uniformly distributed, that means constant, right? Probability of theta is constant. That means then that additional term doesn't play a role anymore, and it's all about this, as we have discussed. So the maximum likelihood, this is constant, then probability of theta, most likely theta given x, is the same as probability of x given the theta, most observed x given the theta, and I'm maximizing this is maximizing that. It's the same thing, and that's the maximum likelihood. So if I then maximize the probability of x given theta to find the theta itself, that can be written also px given theta, right? I'm also adding m here because given the model, but you can ignore the m if you wish. Then this is p from the very basic formula of probability. That is the joint probability distribution of px theta divided by p theta, but p theta is again constant. So this can be also, maximum likelihood can be equivalently expressed as maximizing this joint probability distribution between x and theta. All right, that's again from the probability. And then we have the IID assumption, which helps with the thing, because the joint probability distribution becomes this product due to the independent identically distributed data points. Otherwise, you have to deal with this, not the product itself. So thus, the maximum likelihood estimates theta so that the likelihood function, in this case it would be this joint probability distribution, that is actually proportional to the other one, which is this. It's just and the p theta is the proportionality constant. So it will be just this multiplied scaled version of this, and you are maximizing the maximum maximum likelihood estimate of theta is the maximizer of the likelihood function or its logarithm. It will give the same theta. Logarithm will only have log p as the answer, right? So this is the story essentially. Let's do one example, and then I think that's even simpler, but it's also illustrative. Good to make some. Actually, maybe you can actually do this together with me, and then we can conclude the basics part and go to slowly conclude the basic parts and go to the unsupervised learning. So let's do it together. I'll give you maybe a couple of minutes. This is as simple as it looks, nothing mysterious here. So we assume there are n examples of xi, right? We observe, that's also part of the question, kind of. And IID xi data points, or the set x is like x1 to xn, right? So we observe these data points, and x is a scalar. So as you can see, also x is each xi is a scalar element of R for all I. Right? So done? No? One more minute. So just to give the hint, initially what do you do? You write the log likelihood or likelihood, then take it from there, right? So theta ml, just to write the formula, ml will be then argmax theta, and theta is again the mean-like parameter. That would be then p x1 to xn given theta, right? But because it's IID, it's actually the same as p. So who has done it? Who will help me? Any volunteers? Or you can shout in, like, what am I going to write? So guide me. We do it together. So what do I write here then? So the likelihood function would be then what? L of theta. The likelihood function will be what? The product, right? The product. And then what is pxi given theta? It's px, right? Because this px is actually px given theta. It contains the theta. This is actually equal to px given theta, right? Given theta, that's the px. Of course, given also sigma square, but I'm kind of not focusing on that right now. So that will be then basically p xi given theta is this one. So we need to given theta, and then this is this, right? I'm kind of. So then I actually, because of this is product, what do? I take the log, right? I can write the log likelihood, then log likelihood. The only reason to do this log is, the main reason is this, converting that product to sum, because sum is easier to handle when you take the derivatives. So then I can write this log likelihood as L theta. That would be then log of product will be the sum of log, right? So therefore the sum of log p of xi given theta, which is also as we have written. So I can write it as what then, if I take the log of this, what will it be? Minus first of all, it would be log of the first product term, right? Which is log of 1 over sigma x square root of 2 pi. But then I can write it as minus, then it would be, first of all, sum. Then it would be minus log, because it's the denominator, it becomes 1 over, so it becomes minus, then this is this, go to pi, yep. And then another minus here, because when I take the log of exponent, inside it's a minus, right? Log of exponent becomes minus. So I get this itself, ln x minus theta. This is squared divided by 2 sigma squared. Or I can put the minus here, make these plus. Okay? And then these are all xi's, right? I equals 110. Right? All right. That's it. So then take the derivative, right? Find the log likelihoods minimum with respect to theta. So I find del theta or del theta equals 0. Theta is square here, so you see this is a quadratic function that is a straight minimum. It's a convex optimization problem. The first order condition is also necessary and sufficient. I expect you to write this in the exam, otherwise I'll take points off. Because what if this was not, I'm maximizing this, so it is a minus in front of it, right? So it's an inverse parabola. Therefore, it is a unique maximum. So second derivative has to be negative because I'm maximizing, or I do a max min, right? Turn it to a min, then minus goes away. So this is important to note. Convex optimization, del square L del theta square is negative, right? That's why we need to check this. Otherwise, just taking the derivative equating to 0 is not enough. When I take the derivative, then del L theta dt theta, what would it be? What happens to first term? Goes away, right? Then what do I have left? So I have minus sigma. 2 times 2 goes away. So I've got ln xi minus theta divided by sigma squared equals 0, right? Correct? Good. Then I have n of these thetas, and the ln xi's are summed up, and sigma square doesn't play a role because it's the numerator that needs to be 0. So I got then theta star will be, or let's call it ml, because this will be the maximum likelihood. So that would be then, this minus also doesn't play a role, will be the 1 over n sigma ln xi. I equals 110. But because I have all the n xi's, right, data set, then I can directly calculate this. So that would be the maximum likelihood solution. If I ask such a question in the final, this will be a kind of an easy side of the question, right? It's nothing mysterious here. It won't be a difficult question. By that time, you will know this already, because we will use this again and again. Maximum likelihood is embedded into a lot of learning stuff. So you will know this very well. Very good. It's really nice. So you have a data, and then from the data you estimate the probability distribution parameters based on the distribution that you have chosen log normal. So that there's a model, a priori selection done on the model. We don't know what theta is more favorable, but we already have selected a model. That's important to keep in mind. Okay, the last but not least, it's very important, and then I'll come back to this again probably in different form, is bias and consistency. So when I do maximum likelihood parameter estimation, just like we have done a few seconds ago, we call it asymptotically unbiased if, as n goes to infinity, if I get more and more data, right, my expected value of the estimate goes to the original value, theta 0. And it is called asymptotically consistent if the mean square error also goes to 0, right? That means this asymptotically unbiased is not enough, because it may happen like this. Make a note of this, I think. And then asymptotically consistent is mean square error going to 0. I think I would like to write this down to the notes, because then I post them. So asymptotic biased would be then, sorry about that, asymptotically unbiased is good, because then, expected value of estimate goes to theta true, but can be like this. It's not good. You see, you're fluctuating like crazy. It ends up going to the theta true, but it's not desirable to fluctuate like this. Actually, it doesn't even need to die out. It can be very much like this. The mean is the correct one, but it keeps fluctuating. That's not a good estimate, right? Therefore, asymptotic, consistency, see that the variance, expected variance goes to 0, means actually what I said just a second ago. So even if this happens, it needs to die out, right? Because the mean square error should die out. Here, the mean square error doesn't die out. So mean goes to a constant, but it can go to a constant even though you are fluctuating. So that's important. So we want the unbiased estimate. We don't want to make a mistake, but we also don't want to. We also want some consistency. So as I said, yeah, bias is important. We don't want to make mistakes. Consistency is important because we may be unbiased, but large variations may be observed. This is a beautiful picture. I found it by chance. That summarizes the whole thing. So it is like you're doing bow and arrow shooting type of thing, right? The center is what you want. Okay, you want to hit the center in terms of your theta. But let's look at the possible cases. On the rows, you have high bias and low bias, and then low variance and high variance in the columns. So if it is high bias and low variance, your estimates are consistent, right? But they are off. So you consistently shoot the wrong place. So that means you have low variance but high bias. High bias and high variance is the worst. You're all over the place. You don't know how to shoot an arrow, right? Low bias and low variance is what you want. You want to shoot close. Because it is low bias, you are close to the truth, to the center, but also your variance is small, so you are not shooting all over the place. If it's low bias and high variance, it's also bad, right? So this is the desired situation. This is underfitting and this is overfitting also. There is this interesting connection to underfitting and overfitting. So you are here underfitting. You have a nice consistent, we did it in regression, right? You can have a nice consistent line, but it's way off from the original curve. Or here you get a very complex thing, but you're not getting a good bias when you do the test set, right? So there's also a nice connection to overfitting and underfitting here. And this is, as I say, it's a beautiful picture. Once you get this in the head, you're safe when you also do other types of learning mechanisms. Last is some bias example. You can actually see, this was from the Barber's book. You can also look at that for the details. But the classical estimators for mean and variance when you are given data set is, for example, this is the simplest thing. If you are given a data set and you say what's its mean, the best estimator is just sum them up and divide, right? Just intuitively what you will do. And one can show that this is an unbiased estimator if you take the expectation. This actually is a notation for expectation. So this is actually expected of mu hat. It's a bad notation, but different books do it different ways. This strange bracket is the expectation operator. So you take the expectation of the individual variables, but that's the individual expectation, and then the ends cancel out, so you get the result. This is trivial. And then you can also do a variance estimator. So estimator of the variance is, if you do the intuitive thing, I'm just going to estimate the variance using my mean estimator and using the definition of variance, and then I'm going to do it over the individual data points. So it turns out this intuitive one is biased. So you don't get the real sigma square, but you get an n minus 1 over n sigma square. This is okay as n goes to infinity, but you don't immediately get a biased estimator. So I guess the lesson to learn here is You can come up with some estimators. You need to check the consistency and bias of your estimators if you have certain estimators of some type. Right? All right. It goes to statistics, actually, after this point. It goes deep into statistics. And then I'm not going to go there. So this ends the discussion for me. So let's keep... we can discard. Good, so that's this one. Basics are covered, and then the solutions of the basics, I'm going to post this one, all this stuff today with the notes of the basics, and we go to supervised learning. Should we give a break until the top of the hour, and then we continue with that? All right. So we give a break until 11.
Is the whole point of this section, is it just like you have a set of data points and then you find, out of those set of data points, you find like what's the most likely mean or what's the most likely
You find the
parameters?
Yeah, exactly. You find the most likely parameters of the distribution.
And distribution parameters are mean, standard deviation?
Yeah, it could be anything. Like
Any
in the
parameter.
any parameter. Like in that log normal, it was these thetas, right? And you do a prior selection of the distribution. That would be like conditioned on the model, right? So you kind of condition it on the model by selecting a certain distribution.
When you say model, is it kind of
Yeah,
like you
like
kind of know what it's supposed
No,
to
no.
look
I mean,
like?
in the last question, for example, it's very straightforward. In the last question, you say this is log normal distribution. That's a selection.
So
Why?
it's like
I mean, you
have-
didn't choose normal. You didn't choose Rayleigh. You
Yeah.
chose log normal, and you are trying to find log normals.
So is it kind of like you have a set of data points and you say, oh, the distribution of these data points is fit with this model.
And then I need to find the most likely parameters.
Oh, okay.
But you don't have to use that model, right? So you also make a selection. Just I wanted
You
to
can
highlight
choose another model if you want, and you'll find the parameters
of
those
that model.
models. Oh, okay.
But given the model is usually fixed. You decide to use some certain type of, for example, neural network. Then what are the weights of the neural network? Would be then
We always did it like this in high school.
I'm glad to hear that. It matches
but so
your
this
notation.
is-
I've never done it this way. That's why I always wrote it as X. Okay, so different people, different notations.
Oh no, we always wrote it like this too. But like these formulas to find like variance or mean. So you're saying that sometimes these could be wrong.
No, this is unbiased, but this is not unbiased. So I'm just saying this is unbiased, obviously.
Okay.
So I want us to be careful.
Okay.
Yeah, whether it's unbiased or biased. Yeah, this is fine. It's well known that this is actually also consistent. And I think this is consistent too, but it brings a bias. If n is low, then you're getting the wrong variance.
So basically, it's just saying that
It's
you
just
have
saying
to
this
have a
situation.
lot of data points in order to get like
You
a
always,
correct.
always a lot of data points always help.
Say if you have like only 3 data points, then like sometimes
This
you-
one,
you
this one
calculate
saves
variance.
because it's n minus 1 over n, but sometimes others, if the delta is not dependent on the data points, you may have ongoing bias.
Thanks for that. Clear up.
Good to hear. All right, I think we can start. Now, the important topic of unsupervised learning, then we go to supervised learning. So I will start with clustering, the very famous, well-known k-means clustering, a little bit of PCA, dimension reduction techniques, Gaussian mixtures. I will talk about expectation maximization and close the discussion. So reading list is here. I follow mainly Bishop in most of the cases. The others are more kind of additional material. Yep, so clustering. I already mentioned maybe a while ago in the beginning, first week lectures, about unsupervised learning. So in this case, we have a data set, x1 to xn, and the aim is to find a plausible, compact description of the data, and an objective is used to quantify the accuracy of the description. So this is very vague, as I said before. What does it mean to have a plausible, compact description of data? It may mean very different things in very different contexts. So it's a very vague. And the other thing is, also measuring the success is a bit problematic, right? We can see this from a probabilistic point of view, and we can see, if we look at it from a probabilistic point of view, we may say we are interested in modeling the distribution of the data, Px, right? So this thinking is there is an underlying probability distribution that generates the data. That's a very nice, proper probabilistic point of view, right? The data, it's a very, very probability-oriented view of the world, sees everything as in the axiomatic framework of probability theory. There is a probability generator that generates this X. I find it is a bit overreach. Mathematicians like it, but in reality, from physical, if I put my physical hat, this could be a whole process, real-world process, generating this data set, right? Of course, it's a very complicated data, process, and we may not know enough about it. Then it is appropriate to say, let's make my life simpler and assign a probability model, generative model, then say this data comes from this probability distribution. There are two problems with this. One is it's oversimplifying things. There's a whole physical world going on, and you're putting it, there's a probability distribution. Yeah, okay, that's a bit oversimplifying. It's useful though. And the second thing is, and I forgot the second thing. I was going to say, like you get the probability distribution, but it's a bit oversimplifying, and it will come to my mind. So, and then therefore, you may not end up using the probability theory always. You may use other methods and treat the data as it comes, not because it's generated by an underlying probability distribution. So that's also fine, right? Therefore, there is a whole field called data mining, and it was called data mining. Now the new buzzword is data science, right? So you go to a company, you look at the data coming out of a whole company. Maybe it's a manufacturing company, right? So, and then you look at the data, and then you try to interpret it, find descriptions, as it says here, plausible compact descriptions of the data, and then you give this data to people so they can take actions on it. Maybe they assess the situation, they assess the performance, they want to improve the performance, they want to find the problems with their methods, and all kinds of stuff. So it is quite interesting in that sense. What was the second point I was going to It's really fun. All right, good. It will come to me. So the clustering is actually the most natural things that come to mind when you want to deal with the data, right? There are no labels. It's just the data itself. So I will group them. That's very natural, right? I mean, this goes back to Socrates and Aristotle in ancient Greek and so on. They were looking at the animals, so they said, let's create taxonomy of animals, four-legged animals, two-legged animals, and then you do all these kinds of, you always group things, right, to make the life easier. So you group the set of objects in a way that the objects in the same group, which is called a cluster, are more similar in some sense to each other than those in the other groups, right? So that's kind of a lot of leeway here. Again, what does it mean to be similar, and what does it mean to be, how many clusters are there going to be? They are all open. There are many, many solutions. There are more than one unique solution in this case. No unique globally optimal solution. Different algorithms yield different results. Same algorithm, if you choose a different starting point, gives you a different result. Right? You can do k-means clustering, choose an x0 starting point, and another x1 starting point, you end up with two different local minimum. Now that you know optimization, I can talk about them without worrying about it, right? So because you know optimization, you know what the global minimum and local minimum is, right? So therefore, this all says, if you start somewhere in the hilly landscape of optimization, you end up in a local minimum, you end up in a global minimum. They may differ from each other. So that's kind of also intuitively makes sense. And then sometimes you evaluate them from domain expertise. You look at it and say, if you can visualize it, this makes sense. Or you check if they are fit for your purpose. Maybe you do something with those clusters afterwards, and certain clustering works better for you based on your purpose compared to another clustering, right? The other clustering may give perfect result in terms of some objective function, but may be useless for your purpose. I think you have been playing with the machine learning workshop and you've been observing this a little bit, right? So the workshop gives you a chance to do this. Good. What else? The main categories of clustering algorithms. So I will go, I wanted to mention the sequential and hierarchical clustering. They are not the most popular techniques, but sometimes, all these are goodies. Old classical methods work really well. I'm skipping in this subject a lot of historical methods in machine learning, to be honest with you. But that doesn't mean all those methods are useless. The fact that they are out of fashion doesn't mean they are useless. Sometimes they can become superseded, but some of the fundamental methods are still very good. And even in the worst case, even if they don't perform, if they are superseded by a more modern method, you can still use them as also benchmarking methods. You can use them, if it's a simple classical method, easy to compute, you can use them as a starting point, then you use your fancy method and compare the two, right? So in that sense, it's also good to know the classical stuff. But yeah, as I say, due to time constraints and not to turn this into a history session, I'm skipping a lot of stuff. I didn't want to do that. I will mention quickly the sequential and hierarchical clustering scheme before going to what most people do, cost minimization based methods, which also tie up nicely to optimization. So the sequential clustering, the idea is extremely simple. This stuff is not in Bishop, it's in Theodoridis, one of the other references that has a nice big chunk of clustering in it. Non-surprisingly, because that book was suggested to me by a clustering expert, so you must like it because it has a lot of clustering in that book. So the sequential clustering is you define a distance metric between a data point and the cluster C, feature vector and the cluster C. Then you define, the algorithm works very simply. You define a threshold of dissimilarity. You say, if these 2 points are that different, more than theta threshold, then I should make them a separate cluster. And then you also do this maximum allowable clusters Q, right? So, and then there are many variants. I'm just giving you the simple idea here, to be honest, basic one. You can read more about it. So what you do is you start with you do it sequentially. You start with the first data point, that becomes your cluster center, and then that becomes your first member of your first cluster. Then you go through sequentially through the data points. For each CK, for each clusters, you look at the current point's distance to that cluster, which is the minimum distance to all points in that cluster, right? Closest point. Then if that distance is greater than threshold and I don't have enough clusters now, then I make this one a new cluster, else I add that, if it's close enough to one of them, I add that to that cluster. So, and I do this over all the points. Then depending on how you start, you may end up with certain groups because of this. So it's very, really straightforward idea. I could have included in the workshop, but I didn't. Yeah, that's okay. So at least you know about the sequential clustering. There are many variants. You go one by one. If I'm close enough, that's good. Otherwise, let's create a separate group, make a new cluster, and you need to pre-decide a lot of things here. That's the bad thing about this method. You know, if you ask what is the downside, you need to define theta and number of clusters beforehand. Especially theta is very bothersome, because in k-means also you decide on the k number of clusters, but here you also need to decide what is the threshold for dissimilarity. It's a bit too much to ask beforehand before seeing the data. But it's very simple, computationally trivial to compute. The hierarchical clustering, this is quite more useful and meaningful, and it's still used a lot, especially biology people, as far as I know, use this stuff called dendrograms. I'll come to this. You define this function, again, similarity function, proximity function between clusters, and then there is this function, similarity or dissimilarity function. Dissimilarity function is like a distance function. So you need something to evaluate the distance between the data points. And what you do is actually graphically better explained. You just choose, these don't have to be ordered. It can be ordered in different ways. So for each point, you find the next closest point, and then you bring them together. Then you do this for all, and then this one adds up to that one. So you, among all possible pairs, because this is the odd one, these are the pairs that are closest to each other, then you end up with 1, 2, 3, this one pairs, then this one pairs, so actually you end up with one big cluster. So this is kind of finding almost all possible clusters. I don't think this will scale after a point if you have too many points, data points. But it also gives you a visual picture, this called this dendrogram, and the good thing is you can choose the number of clusters yourself after the fact. Like kind of, if you need a few clusters, if you need 3 clusters, then this is this. If you need 2 clusters, then it's that. If you need 1 cluster, of course, the whole thing, right? Or you can go the other way, divisive algorithms. You can do the reverse. You can start with the big whole, all of the data set, and start dividing it into pieces, and then go to pairs and individuals all the way down, create a huge tree, essentially. This is the inverse tree, and then you create the tree in the other way with the divisive algorithms. Both of them are hierarchical clustering. So these are agglomerative algorithms. You aggregating algorithms. Start from the individuals, you go to the full, and divisive algorithms is you start from the full data set, and then you divide it into pieces. Okay, so again, in certain fields this is useful because it also can be meaningful, but it's not the most popular clustering method. Cost-based clustering methods are the ones that take the most mind share these days, and here the idea is focusing on the distance and similarity metrics between the elements. The previous ones had the same, but now using these distances, I define a cost function. Before I go to the cost function, let's look at these. You know, I mentioned already twice this similarity, dissimilarity stuff. So let's look at those a bit closely before I go to these cost-based methods, right? So let's look at what we can do, right? So if I have given an x and y points out of my data set, what could be the first? I can look at dissimilarity or distances, right? So this could be a very general way of defining distances. I am even weighting individual pairs with a weight vector, and then weighting different dimensions of the x, right? So x is a vector, and then I'm weighting different dimensions of the x, or I can choose them uniform, then forget about the omegas, right? Or certain dimensions may matter to me more. In that case, I can give them more weight, then they play a bigger role in clustering scheme. And if I write it this way with p and 1 over p, p equals 2 will be the well-known Euclidean distance that we know. P equals 1 will be then the max L1 norm or the Manhattan or P equals infinity, then the L infinity norm, or taking the max from the dimensions and use that to define the distance between the two. So that is a quick look at how distances can be defined. And then the point-to-point similarities are inner products. You can use mainly inner product-based metrics, or cosine similarity, right? If you normalize it, then it would be the cosine angle between x and y. So you can use that, or you can use all kinds of trick. There's this Tanimoto measure, which uses basically the dot product, but normalizes it in certain way that this is 1 if they are the same, and it goes to 0 when they are very similar. So it's kind of normalizing it between 0 and 1. If they are very far away, the denominator goes larger and larger, and then similarity measure goes to 0. If they are the same, you see these x minus y's become 0, then 1 over 1, 1. If they are most similar, then you get 1. Good. So this was the dissimilarity or similarity, right? And these are between 2 points. What if you want to do point to set or set to set proximity? Then actually the idea is very simple. Max proximity would be then what is the distance between a single point and the set, and then the farthest in the set would be the max, closest to me in the set would be the min, or I can measure the distance to each point in the set and take their average and say that my distance to the set is given by that average. Again, you have a lot of choices to make here, choosing what type of metric you want to choose. Do I care about the nearest point of the set to me, or do I care about the farthest point of the set point to me, or the average point to me? And set to set would be done 2 sets, and then you kind of again do the same. Is it the closest 2 points, or the farthest 2 points, or the averaging, right? And then accordingly, average or mean, they will be listed like this here. So of course these become more and more cumbersome to compute because you have to go all over the members of the set, right? Okay, there's this question that's kind of nicely makes us play with the similarity versus dissimilarity measures. So let's say we have an S metric similarity measure on X, and it's defined by S, X, Y greater than 0, so it's a positive 1. This is an extra information. Not all similarity measures have to be positive. And we define a dissimilarity measure, which is A over SXY, and A is also positive, right? So it makes sense, right? Similarity and dissimilarity are inverse of each other, or kind of 1 over is a nice way of doing it disproportional, right? If it's more and more similar, then the distance should be smaller and smaller, and vice versa. It says prove that the D metric is a metric dissimilarity measure. This is one of those questions I'm only doing to give you insights. It's not an exam type of question, just to make it clear, right? I will not ask a specific question like this in the not in this form. Maybe much simpler. We'll see. I might ask triangle inequality, but that's also, it should be in a context. It's not a math exam. All right. This is the definition. I wanted to include it from the book. The similarity measure is between 2 points to an R. So you take 2 data points, could be R to the n, 2 vectors. Think of 2 vectors, and then you get a number, distance, similarity, how similar they are. It can be between minus infinity to infinity, and there could be an S0. If there's x and x, it's the same one, then you get a S0. And then everything else should be less similar. You should be most similar to yourself. Also, distance to yourself is 0, right? Distance metrics. And then it should have this, symmetry condition. If it's a proper dissimilarity measure, x, y, y, x. And then it should be S0 only if x is equal to y. You shouldn't get this otherwise. So this is the equality identity. Identity of indiscernibles. So there's the naming for each of these properties. And the third one is close to the triangle, related to the triangle inequality. So let's look at this solution together. So as I said, it's more about going over it and have a discussion. So first of all, let's look at the counterpart of that, and that would be the distance metric. So when do you call mathematically a metric on a set a distance? It needs to have certain properties to be able for me to call it a distance, right? In a space, on a set X, not space, on a set X. So distance is usually between 0 and infinity. You don't get negative distances, right? So it should be non-negativity. And then if the distance is 0, then x equals y. Makes sense. It needs to be symmetric. My distance to you is your distance to me. And then the triangle inequality is x to z is x less than or equal to x to y and y to z, right? Good. So can we kind of get the counterparts of these from the definition of similarity and the thing? Let's go over it, as I say. What do we see here? So we have the sxy greater than 0, and we defined this dxy as a over sxy. A is also positive. That's good. And we claim that dxy is a dissimilarity measure, right? We need to satisfy certain axioms, which are almost the same as the distance, but there's a small change. I will also note that. Right? Since sxy is a positive similarity measure, we have 0, it is between 0 and the maximum, which is s0, right? And s0 is when it is similar to itself, maximum similarity. So that means if I write it down, a over s0 is less than or equal to a over sxy. So it just changes because of this, it becomes this, and that's less than infinite, right? So we have the, basically d is bounded, right? And if we define d0 as a over s0, that means dxx will be a over sx, so that's a over s0, and that's d0. So this is, you see, that's where it differs from the metric. So dxx was supposed to be 0. So this similarity measure is not a proper strict metric, but I can actually subtract it and then make it a metric. Actually, if I make it the definition a over sxy minus d0, then it will be all fine. It will be zeroing out and always positive and so on. It's already always positive, so that's not a problem. But I can shift it to make it, 0 when x equals y. In this case, it is d0. So that's a kind of a thing that's slightly different. Therefore, maybe we shouldn't call this distance metric. It's just the dissimilarity measure because it doesn't zero out. It just goes to a minimum value, which is d0. But we can show that it is symmetric. That's trivial to show. And what else is left is this similarity metric has this property. And because everything is positive, we can also write this. We just substitute the terms from the definition. Then left-hand side becomes this, right-hand side becomes this. This looks complicated, but all a's are positive, so a's cancel out. So you can actually write them as ones. That's not a problem. And if you multiply, how does this become this? Is very, it's not immediately obvious, but actually very simple. All of the d's are positive, so I can actually multiply both sides with dxy, dyz, and dxz, right? If I multiply with all three in the denominator, they cancel these two, you end up with dxz on the left-hand side. And if you multiply all three, this cancels out. The dxy, dyz multiplies here and here. Dxy's cancel out. Dxy, dyz, so dxy's cancel out. You end up with dyz here. Dxy, dyz, dyz's cancel out. You end up with dxy here. So actually, it's a one step from here to here. You just multiply by, let me write it down, multiply by dxy times dyz times dyz, right? So if you multiply both sides with that and divide by a, they're all positive, so it's legitimate, the sign doesn't change. You end up with the triangular, and that's it. Good. All right? As I say, it can become a metric if you subtract d0 out of this, because then all the conditions are symmetricity, and this one, if you subtract D0 from the definition, they are all satisfied, so it's also a proper metric actually. You can turn it to a proper metric from a dissimilarity measure by just subtracting D0 out of it. So that's just to highlight you the close relationship between similarity and dissimilarity. If you are careful, you are doing the same thing, right? Most of the people, as far as I know, uses distance metrics because of this reason. So not many people use similarity, but maybe people deep into clustering might use it, so I shouldn't maybe discard it, because I'm not a clustering expert. So that's a huge field in itself, and quite popular, as I said. All right, so that was a tour of existing basic methods, and then a little bit of tour of what are the possible distance metrics, because we will use them when we do any type of clustering algorithms that are cost-based, as well as others. Here's the problem setup, and that's the k-means clustering. I think it's good to start with a concrete scheme everybody knows about and implemented everywhere. The reason why this is so popular is it's very simple to implement, and it performs reasonably well, so everybody knows, and it's part of the tool chain for everyone. So you have the data set, right? N d-dimensional data points in the Euclidean space, vectors, and the objective is to partition into k clusters where value of k is given. So that's already the only one of the main downsides of this method. You need to predetermine k, as you noticed, right? So in the workshop as well, you need to, and it's not again obvious whether you should have 2, 3, 4, 5 clusters. What people usually do is they just try them. You try different types of clusters and choose the one that you like. So I gave the definition again here for remembering, and then so the clusters are formalized by the vectors. They are the cluster centers or prototypes associated with the Kate cluster. So mu k is the prototype of the Kate cluster. So in this scheme, the prototypes are the mean of the cluster vectors, right? So, and for each point, we introduce also. So this is each cluster has this vector mu k. For k cluster, that means there are k of these. All right, so there are my cluster prototypes, and then for each data point, we introduce the binary indicator variables, r and k. It only says, whether this point belongs to this cluster or that cluster. So r and k is 0, 1. That means r and k has to be 1 for one of the k's and should be 0 for all others. We are assuming here crisp clustering, not fuzzy clustering, so everyone belongs to one cluster at a given time only. If you relax this, if one point belongs to multiple clusters, or if one point belongs to a cluster with some measure that is not 1, 0, then you are in the fuzzy clustering domain. I'm skipping that. Things get interesting and a bit messier there, as you can imagine. But we are going to focus on usually, okay, is this point belonging to which of the clusters, right? Of which of the k? It's a crisp clustering scheme. The problem formulation, as I finally mentioned, the cost-based method is a cost function. So the cost function is over all the points and over all the clusters. R and k gives you 1, 0, which point belongs to which cluster, zeros out others, right? And therefore this double sum actually has zeros out a lot. And then the cost is, I want to minimize the cost of my x to the cluster prototype, right? And then I'm using Euclidean distance here as the distance metric. So, and then this is the total cost. If I minimize this, then find the values of r and k and the mu k, that minimizes j. That gives me a nice clustering, right, based on the Euclidean distance. But then, indeed, the question is complicated. What is r and k? And r and k is, again, 1, 0s. For n belonging to cluster k, then r and k will be 1, and all other r and j's that are not k, it will be all zeros, because I'm only belonging, nth one belongs to cluster k. Okay? And then we need to also find the mu k's, the prototype vectors associated with each of the clusters, right? The k-means, as the name indicates, this mu k's, as prototype, I choose the means of those clusters. That's why it's called k-means. So first, let's look at this. This is actually mixed integer programming, because one of the decision variables is an integer, right? It's not a nice, clean convex problem. So therefore, because it's a mixed integer optimization, we solve this through, and there is no straightforward, easy way of solving these mixed integer programs. We do it an iterative algorithm, right? So we first choose some initial values for the mu k, some cluster centers. Actually, we can choose very random points. And then once we do choose we first choose the k, first of all. I have, let's say, 5 clusters. Then I choose, I can choose even randomly some initial prototypes associated with these clusters. They shouldn't be the same, of course. They should be different from each other. So I've got mu1 to mu5. And then what I do is minimize the j with respect to the r and k, keeping the mu k fixed. So I keep these mu's fixed, and then I find the points that are closest to those cluster centers and assign them to those clusters. So I already clustered everyone. That's called roughly, this is called informally an expectation stage. But then the second stage is, now that I have done this, I choose the new mu case to minimize j while retaining the assignments that I have made. So assign first, start with some mu's, assign all the points to the clusters, then now that you have made the assignments, take the means and determine these prototype mu's by the means of those clusters. And repeat until convergence. Funnily enough, this converges always. I will actually go to the detail of it. The catch is, though, although this converges, this may converge to a local minimum. So it is guaranteed that it converges, but it is also well known that you most probably will end up with a local minimum, not the global minimum. So that's a problem. So if you want to have a better result, maybe you choose a different starting point, repeat it, and maybe you get a better cluster. Because each starting point will give you a different local minimum. And it's very hard to know whether it's the global minimum or not. Again, more formally, I want to minimize the j with respect to r and mu, because r is a r is an integer, r and k is an integer vector. Therefore, I cannot take the derivative with respect to r, right? Because it's an integer. So I do this two-step process. One step, given the mu case from the previous step, I make the assignments based on the closest distance, and I assign individual points to the closest distance. Then once I finish the state, I go to the second state. Now I do this minimization with respect to mu k, now that the r and k's are constant. And that is actually, if you take the derivative of, now this is proper convex optimization. If you take the r and k's as constant, this is convex. So this actually is quadratic. Then the solution is simply setting the mu k equal to the mean of all data points assigned to the cluster. So that's also one of the reasons why it's called k-means. Good. So I think this is a really beautiful visualization. So we have k equals 2, and look at the step by step. Let's go over it. So randomly blue, because k equals 2, we can color code it to red and blue, right? And the green ones are my data points. Initially, data points are not assigned to anything, right? And I'm using Euclidean distance to define. Remember, this is the algorithm. This is my j. This is the assignments, and this is the Euclidean distances, right? And the two steps are these. First, I need to, given the mu's, I need to assign them to the closest ones, argmin distance, Euclidean distance. And once I assign them, now I need to, once I assign them, I have now k clusters. For each cluster, I define the prototype mu's of that cluster by doing this mean. I take the mean of the x's and divide by the number of the element. This denominator is nothing but the number of elements, data points in that cluster, specific cluster. So k equals 1 maybe has n1, and then that's because these are 1 zeros, you sum them up, you get those that belong to the kth one. Right, so here for the 2, I start with the first step. These are initial randomly chosen ones. Now, the closest ones will go to the blue, closest ones will go to the red. Actually, that's a Voronoi tessellation, right? We did that a little bit. So in 2 dimensions, it's easy to do. So you see immediately, this is my cluster 1 and this is my cluster 2. Now what do? I have done the Rn step. Now I need to do the mu's, prototypes of these clusters. So now I have all the points, and if I take the mean of these points, blue points, I end up here. And if I take the mean of the red points, I'm here. So you see my mu's have moved from their initial. So it's not easy to see, but blue x is here and red x is here, okay? Now the second step. Now, given these, now I keep the mu's, right? Now I need to do reassignment. Based on the mu's, what are the closest ones to the mu's? And then that will suddenly do a different Voronoi tessellation. My blue points are these now, and red points are these here, right? Now that I've done it, I need to take their mean, and then this moves the x here and the other x to the center, where the crowd is, right? And you can repeat it, refine it, and then this is here you go. You got some nice clustering out of this, right? So with k equals 2 clusters. Initially, I had only this. The method gives you a nice local minimum of my cost function, and that's it. Right? Could have been 3, could have been 4. The cost function monotonically decreases via EM, because at each state, at each step, or pairs of steps of the iteration, each iteration of the algorithm, each iteration has 2 steps, each iteration finishes. At each step even, you are decreasing j, right? You are not increasing j. There is no possibility of increasing j. So it is monotonically decreasing. But as I say, it monotonically decreases maybe to a local minimum. This doesn't mean it's the global minimum. Maybe, j is defined in a very large space. There may be a lot of local minima depending on how you start and so on. All right? That's the famous k-means. Actually, this question goes a bit deeper into this property of k-means, why it must converge. So we've discussed the k-means algorithm. This is just a discussion, repeating, and this is also repeating. The question says, argue that as a consequence, the k-means algorithm must converge after a finite number of iterations. That's interesting, right? As I said, it must converge. The catch is it doesn't have to converge to the global, it converges to a local. Why is that? Actually, it is, I will just put an argument. It's not a full mathematical or logical deep solution, but it's just one slide argument here. So this is the cost function, just to keep it in front of us, right? So the main thing to realize is the algorithm will never change from a particular assignment of data points to the prototypes, axis to the mu case through RNK mapping, unless there is a new assignment that has a lower value of j. So you will not go to an assignment that increases the j, right? You are always optimizing at each step and each iteration. At each iteration and each step of each iteration, you always minimize j. First you minimize with respect to r, then you minimize with respect to mu. Then again you minimize with respect to r, you minimize with respect to mu. So that's actually a very straightforward way of ensuring that j never increases. That's good. That actually is the key here. One has to say that. The second thing to realize, and that's actually not immediately wasn't obvious to me either, there are only finite number of assignments. So, and that is called a Stirling number of the second kind. I have the Wikipedia link here. So that is the number of ways to partition a set of n items into k non-empty subsets, right? And that's exactly what we are doing with k-means, right? So we have n data points and k clusters, both of are predetermined. I'm giving the data set and I decide on the k before starting the iterations. So that means actually there are only so many ways of assigning, right? That is already finite. It could be a huge number, it's finite though. It's a combinatorial number. So because of this finiteness, you actually start with the iterations, and because you are never going to increase j, even if you try many of those possible partitions, you will end up with a finite number of, in the worst case, you may do the Stirling number, the all possible combinations, but you cannot travel the all possible combinations either, which is also finite. You will end up with a finite number, probably in most cases less than the Stirling number, but you will end up with a finite number of iterations, and that's the end of the argument. So the bottom line is, even if you tried all the combinations randomly, it would be finite. And because you are not doing that and you are minimizing j at each stage and not increasing it in any way, you will end up with possible sequence that will be much less than that finite number. So it will be still finite, so it converges in finite number of steps. And but I put this. Still keep in mind that convergence is to a local minimum, possibly to a local minimum. It could be global as well if you're lucky, but you are not guaranteed, right? And that's the thinking behind it. So it's kind of there's also a mathematical foundation to why it goes to after converges after a finite number of points. All right, let me see. So. Should we start with a little bit of principal component analysis? Maybe. Maybe I'll give you the initial kick and then we finish it tomorrow. So the idea is dimension reduction. Actually, yeah, this is good to discuss as a closing discussion. This is conceptual. Let's keep it at a conceptual level. We have the data vector, right? X. And these days it's very fashionable to take a big picture and create a vector out of it. That's actually very... If you look at it from classical image processing point of view, this is borderline heresy, because in the old days it was all about image is a special structure, it's a matrix, and I have my neighboring pixel, and then all these deep learners do is, I don't care, I'm just going to create a vector out of it and give it to my deep learner. So if you're an image processing person of the old kind, you should be properly horrified by this, because I'm killing all the things that makes an image. Same for the audio. You can take an audio file and make a huge vector out of it, and that's what they do in the deep learning. It's really funny business how things change, right? But once you do that, you end up with a huge vector, like hundreds of dimensions, thousands of dimensions, right? Or you may not do it, in these domains, but you may have a legitimate problem where the dimension is very large. DNA sequence. That's huge, right? That's a very large vector. DNA of a person or a gene or gene sequence, they can be very, very large. So very large dimensional spaces. Can you imagine how a 4-dimensional space looks like? Or 5, 6? We need to go to meet some aliens if they can do it or not. We human beings cannot do it. So it's really funny, right? So we are very limited. So we cannot even imagine. And all of our intuition comes from 2, 3-dimensional spaces. What does it mean to be near? So I am actually nearer to the front, right? In this, actually it's a 2-dimensional space. Nobody's in the air, so it's in this plane, right? I am closer to the front, and I am distant to those who are sitting in the back. All this intuition goes away in 100-dimensional space. Maybe I'm all equally distant to you. So actually that's one thing you should keep in mind. Most of these problems are in high-dimensional spaces, and you should check out your intuition at the door. Don't bring your intuition at all. But we are humans, so we need to overcome this curse of complexity, curse of dimensionality, very harsh dimensional. The other problem is we cannot imagine it, we cannot visualize it. That's bad. But there is also implications for classic algorithms, many classic algorithms, when you give a 100-dimensional problem, they literally choke. You know, they cannot do anything. Computationally, they blow up. That's called curse of dimensionality. The complexity of the problem, increases. And also, even if my algorithm can handle it, of course, it's desirable to remove redundancy and, make it computationally simpler. If I can do it in 1 minute, why should I do it in 2 minutes? So the idea is that if I decrease the dimension of data, then I can overcome this curse of dimensionality, remove redundancy. It's not in this slide because it's not about that, but if you can also map it to 2, 3 dimensions in some way, then you can use the human. You can put the human into the loop, because if you map it to 4 dimensions, human is out of the loop. But if you can map it to 2, 3 dimensions, then you can visualize it, and maybe visually you can use human brain as a pattern recognition tool and put the human to the loop of your problem, right? Feature selection, the classical way was domain expertise and other methods. And then there are also automated methods as well. So you can use domain expertise. As I said, if it's an audio file or image file, you can use the properties of these domains to reduce the dimension. Or you can use more generic feature projection methods, of which the classical one that I'm going to talk about is the principal component analysis, the very well-known one. Then there are PCA variants, and there are autoencoders. Again, deep neural networks can be used again like this. So PCA is a good one that does essentially this. This is a good 3 to 2 dimension mapping. So if my data points are these red dots, right, in the 3-dimensional space, if I map it to 2 dimensions, it would be a plane. Maybe my plane is that gray plane. Then what does it mapping mean? It just map them to those black points on that plane, right? So that's what I mean by dimension reduction technique. This is a nice picture. So, and that's one of the few possible pictures, because I can do 3 to 2 or 3 to 1 or 2 to 1, and that's it. As a human being, that's all I can visualize. So you need to imagine you have 100-dimensional and then you're mapping it to 50-dimensional or something like that, right? Unless you go back to 3 dimensions, you cannot visualize it. So this is kind of what's happening. Again, bringing it to our human understanding. So PCA is widely used for dimensionality reduction, also data compression, which is out of our scope, feature extraction and visualization, if you can bring it down enough. And the goal is to project data onto a space having dimensionality m less than d. Because the goal is not always visualization, just the goal could be simplifying the computational load of your algorithm. M may be much larger than 3, but if the D is, like, say, 1,000, and I map it to 100 dimensions, I'm getting pretty much mileage out of my mapping, right? So, and how am I going to do that? As you can imagine, there may be many, many ways of doing this. How am I going to choose that mapping? Is it going to be a linear mapping or nonlinear mapping, first of all? And if it's going to be a linear mapping, what type of a matrix am I going to use to do this mapping? If it's a nonlinear mapping, what type of a nonlinear mapping am I going to use, right? So it's an x to y. Y is m-dimensional, x is in d-dimensional. I want to take the x and map it to y. It could be an f of x to give the y, which is f is nonlinear, or PCA is linear, so you get a you get a matrix essentially, like matrix like dimensionality reduction. Then it's an m by d dimensional matrix, and that would be a linear mapping, right? If it's a linear mapping. If it's a nonlinear mapping, that's a nonlinear mapping. What criteria am I going to use to choose these mappings? That's the question that will be a little bit answered at this stage. So that's what we are going to talk about tomorrow, and hopefully tomorrow I will finish this part, and then after you come from the break, we will do the, while you're doing still the machine learning workshop, we will still do the supervised learning part, machine learning, and then from there we go to, as I said, the week after, a couple of weeks for neural networks, and then 1.5 weeks in plus the guest lecture, the last words and the reinforcement learning. I want to do a little bit reinforcement learning as well. All right? So very good. See you tomorrow. And then, yeah.